Welcome back. So today the lecture is going to be on function composition. But first, let's consider two functions f and g. Here we have a graphical representation where the input of f is the x-coordinate and the output of f is the y-coordinate. And here we have a table with the input and output of g. So for example, we could ask questions like, what is f of 0? Well, f of 0, it turns out, is 2, because that's the y-coordinate corresponding to an x of 0. And we could also ask questions like, what is g of 2? Well, it turns out g of 2 in the table, the input is 2, the output is 4, so we'd say this is equal 4. So far, so good. We know how to do that stuff. Now today, I would like to ask the question, what is g of f of 0? Now, the way I said it perhaps indicates the order in which we want to do these operations. So the inside, this is g of, think about it as parentheses, f of 0. So we want to do f of 0 first. Well, we already know that f of 0 is 2. So this expression for f of 0 is actually equivalent to simply the number 2. So we could rewrite this as g of the number 2. But that means use the number 2 for the input of g, and we already know that that output is 4. So we understand that g of f of 0 gives a value of 4. But what does that actually mean? So that means from the middle, we use 0 as the input for f. So now we're here. We have an output. That output, 2, becomes the input for g. So we would look for that number over here, and we say the final output is 4. So if we were to do something slightly different, and we said, what if I would like f of g of 2? So now, looking from the inside, 2 is the input for the g function. So we look for 2 over here. That gives us an output of 4. So that means this g of 2 will become the number 4. We can rewrite this now as f of 4, and 4 is the input for f. So we would look for 4 as the x-coordinate here. The output is the y-coordinate 1. So we would say this is 1. Okay. Now there's a separate type of notation to indicate the same thing. And when we say g of f of 0, we sometimes choose to write this as g with a little circle for of f. And we put parentheses around that, and then we say 0 here using the input. So this means take the input of 0 and then put it into f as an input, and then whatever output you get, put that as the input of g. Now let's consider some function rules. So you can see on my screen that I've taken these two functions and defined them in my calculator, so perhaps I can use them later. So what if we want to find something like h of j of 2? So from our previous discussion, we understand that 2 needs to become the input for j, so we can take 2 and put it in for all the x's here. So I'm going to leave the h still written, and inside I'm going to write the expression j of 2. If we evaluate this, we get negative 4 plus 4, 0, plus 4 is now positive 4. So that would become h of positive 4. And we need to take that 4 and put it in as the input for h. So we're going to put the 4 for the x, 4 for the x, which makes it 3 multiplied by 4, subtract 1, is now 11. Okay. Now there's something worth noting at this stage, that here, right, 2 is in parentheses, but it doesn't mean j times 2. This means j of 2, so 2 is the input. Here, in this parentheses, all of those numbers put together are going to get a number, which is 4. That's not h times 4, that's h of 4. 4 is the input. But when you use parentheses here, for example, this is 2 times 2. This is 3 times 4. So we have to be really careful. When we're using numbers, when we're using variables, parentheses are used for multiplication. But when we are using function notation, the parentheses do not mean multiplication. So for example, in this case, I can't say ridiculous things like, well, let me divide by h so the h cancels. That's not a thing. This is h of 4, not h times 4. In the calculator, let us evaluate these to confirm that the calculator is doing what we expect it to do. So if I were to take j of 2, it gets me 4. that is the inside right here, j of 2 becoming 4. If I take h of 4, I will get 11, as expected. But the calculator can also do the composition like this, where it understands the order of operations, inside first, then outside. It will get me the same output. Okay, perhaps that's going to be useful later when we want to do things with the calculator. Now, what if I decided to say j of h of 2 instead of h of j of 2? So the order is different. The 2 is now going to become the input for h. So let's try that. I'll write the j, and in the parentheses, I will take 3 times 2 minus 1, which is 5. This becomes j of 5. So I take 5 and make it the input for j. So I'll put the 5 in for all the x's here. This is negative 5 squared plus 2 times 5 plus 4. This is negative 25 plus 10 gives you negative 15. Plus 4 is now negative 11. Okay. If I do j of h of 2, negative 11. Okay. So now that we understand the calculator is doing what we expect to do, perhaps we can test other cases. For example, what if I look at this and think to myself, well, if I switch the order of h and j, does that just make my answer negative? Well, now we can test it. What if I take h of j of 3, for example? That gets me 2. Now, if I switch the order and say j of h of 3, am I going to get negative 2? No, not at all. Switching the order doesn't necessarily make the output negative. And of course, switching the order is not always going to make the same output. So be careful. Switching the order in function composition doesn't generally give you anything easy to deal with. They're simply different ideas. Order is very important. What if we ask, can we write a function rule, meaning a formula, for h of j of x? So perhaps h of j of x like this. Well, perhaps we can, right? Because j of x is that entire expression normally. And that entire expression is going to become the input for h. So we would take that whole thing and put it there. So this is what it's going to look like. I'm going to say h of, and j of x is going to become negative x squared plus 2x plus 4. And this entire expression must become the input. So I will replace the x with this, replace the x with this, and I will have 3 multiplied by negative x squared plus 2x plus 4, subtract 1. And distribution gives me negative 3x squared plus 6x plus 12 minus 1 is plus 11. This is the function rule for h of j of x. Now, just to be interesting, why don't we do the reverse order and find a function rule for j of h of x. So the interior function, this is an expression 3x minus 1. So I would say this is j of 3x minus 1. So 3x minus 1, the entire expression will become the input for j. So I'm going to take this expression, replace x, replace x, replace x. This is negative, parentheses 3x minus 1 squared, plus 2, parentheses 3x minus 1, plus 4. And if I expand this, I will get negative 9x squared should be plus 6x minus 1, plus 6x minus 2, plus 4, which finally simplifies like this. And we notice immediately that this is not the same as that. They're completely different. So switching the order does give us something very different. Okay? But in the earlier discussion, I mentioned perhaps that this could be rewritten as h of j of x, where h of j represents the composition, h of j, where I've taken these two functions and combined them in a way that I have created a single function rule that gives me h of j. So I can actually think of this as if I take a function and compose it with another function, the combination of those two things is going to be a function. I suppose I should say composition of them instead of just saying combination, because there are other ways you can combine two functions. Okay. The same thing here. If I say j of h of x, then I can write this as j of h of x, And this would be the function rule for j of h. And we can try things. For example, on the screen you say h of j of 3. So what if I wanted to do h of j of 3? Instead of plugging the 3 into the j, taking that output and plugging that into the h, perhaps I can just plug the 3 directly into the function rule for h of j of x. So that would be negative 3 times 3 squared plus 6 times 3 plus 11. That's negative 3 times 9 is negative 27, plus 18 is negative 9, plus 11 is 2. So this is 2. And we see on the screen here, h of j of 3 is indeed 2. That's what the calculator told us. And if we trust it, life is good. Now, what if I want to consider j of h of 3? Instead of taking 3, making it the input for h, then taking the result and making that the input for j, I can short-circuit the process by saying j of h has a function rule that's that. So I can take the input 3 and put it in for all the x's. That would be negative 9 times 3 squared plus 12 times 3 plus 1. So that's negative 9 times 9, which is negative 81, plus 36, which gets me negative 45, plus 1 is negative 44. And that is indeed what we see on the screen here with j of h of 3. So there's a lot of notation happening, but really at the end, what I want you to take away from this is that this notation and this notation really mean the same thing. And you don't even have to distinguish it as, if you see this, you have to do it in 2 steps, but if you see this, you can only do it in 1 step. No, they're completely identical. Let's go back to the functions f and g we defined earlier. And now let's imagine we want to say f of g of, we'll go with 1/2 now. So if I take the number 1/2 and try to put it as the input for g, I realize 1/2 is not part of the domain. So here, immediately, I get an undefined result because we have a domain error. Now, what if I say f of g of negative 1? Well, that means negative 1 is the input for g. So I go over here, I find negative 1, the output is 5. So now I understand this is f of 5. So I'm supposed to take that as the input for f. That means use 5 as the x coordinate and find the y coordinate. Go over here, and there's no point at x equals 5, because 5 is not part of the domain of f. So once again, I get an undefined result. So now we have to think, what is the domain of f of g? Because theoretically, we can represent f of g as a single composite function. Well, one thing that could happen is that the number we use as the input could not be in the domain of the first function g, the inner function. Okay? But in this case, negative 1. Negative 1 is in the domain of g, but negative 1 itself is also in the domain of f, meaning if I make x negative 1, I can get a y value. So the issue wasn't that the input negative 1 is not in the domain of either of these. The issue is that if I take the output g of negative 1, then that 5 is not in the domain of f. So if we try to illustrate this, this is what it begins to look like. We say, all right, the domain of g, we can put on a number line, negative 1, 0, 1, 2, 3. And these are all isolated points. I'm not going to have an interval here. And then this is going to give me the range of g. Well, the range of g is going to be the list of those values. So I'll have a negative 2. I'll have a 1, a 2, a 4, and a 5. So those isolated points, no intervals. And then if I want to think about f individually, so if I write the domain of f, and I bring this down and look at it. So the domain of f is going to be all of the x values between negative 3 and positive 4, but including the endpoints. So I can write that as an interval from negative 3 all the way to positive 4, close circle, and shade in between to indicate the interval. And then the range of f is going to be the interval from -1 for the lowest y value up to the positive 3 as the highest y value. That interval is going to be from -1 all the way up to 3, close circle, shade in between. Okay. So to get the domain of f of g, the composite, what I have to think about is, number one, I have to pass the domain check for g. I have to have an output, g of x, which means, first of all, the only allowed values to start with are those. If I don't have one of the numbers that's in the domain of g, I'm automatically going to get an undefined output. Okay. So first of all, I have to be one of those numbers. But then, after I get the outputs, those have to end up in the domain of f. So I have to sort of superimpose these and take the intersection. So I'm going to go ahead and draw this on the range of g. So that's going to be an interval from -3 all the way to 4. So the intersection of these is going to be the common -2, 1, 2, and 4. But notice that 5 is not in the intersection. So we would say if we get an output of 5 by using g of x, then that is going to fail the domain check when we go to f, which means we work backwards. Whatever input over here caused this output of 5 is no good. Well, if we look at the table, if output is 5, the input is -1. This is the culprit. So this is not in the domain of f of g. Okay? Now let's imagine we want the range of f of g. So we start with the domain of f of g, which is those 4 values, and we say the outputs of those 4 values are those 4 values which satisfy the domain of f. Now we have to take those 4 values and run them through f to see what part of the range of f we're actually going to get. So if we look at this, f of -2, I'm going to cheat a little bit and just tell you that this point is -2, 0. You can calculate it by using the slope. So that means when x is -2, my y value is 0, so that means the output is going to be 0. Okay? So 0 is going to happen. And then when my input is 1, my x value is 1, my y value is 3, I'm going to get that value at 3. When my input is 2, I'm going to get an output of 1, so the number 1 is going to be part of the range. And then finally, if I use 4 as the input for f, the output is 1, so I'm going to get a repeated value of 1. So finally, we would say the range of f of g is the set of numbers 0, 1, and 3. Let's come back to h and j and repeat the analysis. So if we look at the domain of h, unless we have restrictions stated, that's going to be all real numbers. I can shade the entire number line, or I can simply write the set of real numbers. Now this is going to produce a range, and we say that is a linear function, which means if you think about the graph is going to be a line. So I can sketch that really quickly up here. That would have a slope of 3 and a y-intercept of -1. So notice that all of the y values that are real numbers are going to get covered by this line. It's going to extend indefinitely downward and indefinitely upward, and no y value is going to be missed, which means the range of h is all of the real numbers. I can shade the entire number line, or I can just write all real numbers. Sort of simple. And for j of x, we say the domain of j is going to be all real numbers unless stated otherwise, because I can plug anything I want and square it and add it to 2 times itself, okay? So this is going to be all real numbers. And then, of course, the range of j requires us to understand the graph a little bit. So at this stage, I don't need you to remember how to graph a parabola. I'm going to go ahead and pull up a graph tab, and I'm going to say this. I could type in -x squared plus 2x plus 4, or since I've already defined my j of x, I can do this, and it will give me a graph. So I can understand this top value right here. If there's any doubt in my mind, I will do an analyze graph, find the maximum, from there to there, and I understand the y value is 5. So the range is going to be from negative infinity up to 5, and it's going to include 5. So it's going to be this. I can write this as an interval negative infinity comma 5 if I desire. Okay, so the deal was, whatever the range of h is, it needs to overlap with the domain of j in order for the function j of h to give a valid output. So let me write that out carefully. If I have j of h of x, so that means x is going to become the input for h, and then the output of h of x, is going to become the input for j. So if the number that shows up in the range of h doesn't show up in the domain of j, then you're going to get an undefined output. But in this case, the range of h and the domain of j completely overlap. They're both all real numbers. So here's the best part. That means all of the domain of h is okay, because there's nothing here that I have to backtrack and worry about not being okay. So the domain of j of h ends up being all real numbers. And then because I'm using all of this, and I get all of this, and that means I get to use all of this, I'm going to get all of the range of j. So the range of h of, sorry, not h of j, j of h is going to be negative infinity, comma, 5. Okay, that seemed a little bit less bad, but I have an even better proposition, because we were able to say j of h of x equals, and I can pull it up right here. Remember, we found by taking h of x, so we said h of x is an expression that was 3x minus 1, and we took that expression and used it as the input for j. And that gave us this negative 9x squared plus 12x plus 1. Well, that's a quadratic. So we can immediately say, oh, the domain of j of h is all real numbers. And then we can ask, what is the range of j of h? Well, this is a quadratic. It's a parabola, if I graph it. And at this stage, I don't need you to know how to graph a parabola yet. So I'm simply going to go negative 9x squared plus 12x plus 1. And I see that the maximum value is going to be 5. So I know that it's going to be from negative infinity all the way up to positive 5, and that is the range of j of h. And I get the same result here, right? So I went through the sort of lengthy analysis that we used for the f and g, and we got a result. But if it's possible to simply write j of h using a function rule, then you can go directly to finding the domain and range as long as there were no restrictions in the intermediate steps to get there. And perhaps you'll see some of that in the problem set. The last thing I want to do today is come up with a very cool result. So I want to consider a generic function f, not the f we defined earlier today, but just a generic function called f, and its inverse function, f inverse. So the deal is, if, right, we say f of x equals y, then the x is representing the input, and the y is representing the output. Then we can say that f inverse of y, so I'm taking the output of the original and using it as the input for the inverse. What I should get here is the input of the original, right? I'm switching the input and output. I'm working backwards. So what if I want to do something like f inverse of f of x? Well, in order, f of x is going to produce an output y. So I can rewrite this as f inverse of y. Then f inverse of y is going to produce an output of x. So if I jump directly from beginning to end, I could write this result down. I could write f inverse of f of x is equal to x. Okay. Now what if I want to do it in the opposite order? If I say f of f inverse, and instead of putting in the letter x here, I'm going to put down y because that's already on the page and perhaps that's familiar to us. So I'm going to put down a letter y. Is that okay? I mean, I can put any letter I want. Really, an input can be a number, it can be a letter, it can be an expression, whatever I want as long as I stay consistent. So f inverse of y is going to give me x as the output. So that's f of x. And then f of x is going to produce an output of y. So that means this is equal to that. The input at the beginning is equal to the output at the end. Now, what I'm going to do next in red is I'm going to rewrite this, except now in the inside I'm going to write x because we tend to write x by default when we don't have other things we need to write. So the y here comes out to the same y over there. And this could have been any letter. So I could have written an A here, a B here, I don't know, a weird, interesting Greek character. But if I chose to write x, then the output is going to be x, right? Consistency. Now, if I look at these, not only are they the same as each other when the order is flipped, because earlier we saw switching the order doesn't necessarily give you the same result. If I start with x in the very inside input, then I get the exact same thing at the end. If I start with x in the inside input, I get the same x at the end. So this means that the function f inverse of f, which is that up here, and the function f of f inverse in that order are both the identity function, meaning whatever you start with is the same as what you end up with. And in fact, that allows us, technically I haven't justified that allows us, but it ends up allowing us to use this result to prove that certain functions are inverses of each other. So let's imagine I came up and gave two function rules, f of x equals 1/3 x plus 4, and g of x equals 3x minus 12. And I wanted you to prove that these functions are inverses of each other. You could prove this by saying, what if I take f of g of x? So this is g of x, and that becomes the input for f. So I would write that as 1/3 3x minus 12 in the parentheses for the x plus 4. But if I simplify this down, I get 1/3 times 3x is just x. 1/3 times negative 12 is minus 4. Then plus 4, those cancel and I just get x. So we just proved that f of g of x equals x. And it turns out this constitutes a proof that f and g are inverse functions. So I can say that g of x is the same thing as f inverse of x, and I can say that f of x is the same thing as g inverse of x. So f and g are inverses of each other. And this is a very cool thing that you can do with function composition. All right, well, thank you for tuning in. This is the end of today's lecture, and I hope to see you again next time. Take care.